Okay, so we'll continue with chapter 1, and in section 1.5, there's only a couple of things I want to mention. We're going to be discussing significant figures and rounding off. For the problems that you're going to be doing in this class, I'm only going to require you that you round off to two significant figures, or to the hundredth. Like in this example, 22.10 will be an answer you will have. No more than that. But there's a couple of rules when you're running off. And again, you probably remember this from your high school math. And this is basically the rule here. And it says that the procedure is to know the digit following the last to appear in the rounded form. Add a 1 to the last digit if it's greater than or equal to 5, and leave it alone if it's less than 5, right? So that's really the general rule. And so, for example, if you have a number of 3.186, if you follow that rule, and if you rounding off to two significant figures, the 1/8, then you look at the number right after the 8. And since the number right after the 8 is greater than 5, then you're going to add 1 to the 8, right? You make it into a 3.19. And if you look at 3.19 and you want to round off to one significant figure, then you look at the number right after the 1, which is 9, and that number is greater than 5, so you will then add 1 to the 1, and it becomes 3.2. So this is a good example of how the rule works, right? Since in this case, the numbers that we wanted to round off next are greater than 5, then we just add 1 to that number. And then this depends on the level of precision you're looking for. So again, if you look at this example here, example 1.1, if we add in this three numbers, the result is 536.656. And if you want to round off to one significant figure, then you look at the 6 in this case here, and the number following that number 6 is 5. So since it's equal to 5, then you're going to add 1 to the 6, and it becomes 536.7. Okay, that's the rule. Same thing here. If we add in these numbers here, and if you look at the result, 0.0494, if you round it off to two significant figures, because it's the it's the lowest one here, it's two significant figures, right? So you always round off to the one that has the least number of significant figures if you add in more than two numbers. So in this case, if the final answer you wanted in two significant figures, then you look at the two figures right after the decimal point, 0.4, right? That's what you're going to approximate to. And since the number following after 4 is 9, is greater than 5, so you're going to add 1 to the 4, and the answer becomes 0.05. Very simple rule, but again, and there's a couple of examples, right, to two significant figures, or the hundredth place. You notice here the 1 is followed by a 9, so that 1 is going to become a 2. In this case, the 5 is followed by a 3, so there's nothing to add because the 3 is less than 5. And so the 5 remains a 5. Okay. All right. So again, make sure that you can practice using these examples and understand what's going on. One more example here. You round off this answer to tenths place, to hundredths place, and to thousandths place. So tenth means one significant figure, hundreds mean two significant figures of accuracy, and thousands means three significant figures of accuracy. So now, if you do that, then if you round off to one significant figure, again, you look at the 8 is followed by a 7, so that 8 will become a 9, right, in this case. And then you look at to two significant figures, you look at the 7, and that 7 is going to become an 8, right, because the 6 follows it. And to three significant figures, it's not going to change because the number after 6 is 4, so it remains the same. Okay, so again, those are the simple rules just to round off, and for most practical purpose in this class, unless asked differently or the problem asks you differently, you're going to be running off to two significant figures, so hundredths place, like in this case. All right. Now we look at section 1.6, and this is really an important section. And it may be that this is something you haven't really done in high school, or if you have done it, you need some refresher. But it's going to become really, really critical for us to be able to deal with powers of 10, because when we start working with problems, we're going to be dealing with just powers of 10 in these problems. Okay. So the rules are simple. And you may notice this, right? Because the numbers when it's base 10, if you look at the number, like in this case, if you look at, excuse me, 1 minute. If you look at this number, 10 to the 0 is always 1, right? Any number raised to the power of 0 is always 1. Doesn't matter what the number is, right? 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, right? So what that means is, as usual, as you should know, the exponent means the number of zeros that follow that number, right? So the number of zeros in 10 to the 1 is 1 0. The number of zeros in 10 to the 2 is 2 zeros. And the number of zeros in 10 to the 3rd is 3 zeros, and so forth, right? 10 to the 4th will be 4 zeros, and so forth. When we divide by 10, then the exponent becomes negative, right? So in this example, 1 over 10 is 0.1, 1 over 100 is 0.01, and so forth. So 0.1 is 10 to the minus 1. 0.01 is 10 to the minus 2. The minus exponent indicates the number of significant digits after the decimal point. So for example, 10 to the minus 1 means that after the decimal point, there's only one significant digit, or one digit. 10 to the minus 2 means that there are two digits after the decimal point. 10 to the minus 3 means that there are 3 digits after the decimal point, and so forth. Right? You also notice that in this notation, 1 over 10, the 10, when you bring it up, becomes negative, the exponent, right? And we'll see one of those rules, how that happens. Okay, so that's important. So in this notation of powers of 10, if you move to the right, indicates a positive power of 10, and if you move to the left, it indicates a negative power. For example, 10,000, right? If we move the decimal point 4 places, right, in this case, it becomes a positive 10 to the 4th, okay, over to the right. And if we move, if you notice here, if you move this decimal point from this location 1, 5 places to the left, it becomes a minus 5, okay? So moving to the right indicates a positive power of 10. Moving the decimal point, right, to the right means having a positive power of 10. And moving the decimal point to the left means having, or implicitly having, a negative power of 10. All right, so that brings us to some very important relationships here with powers of 10. The first one, which is very important, if you have a number n being any number, can be positive or negative, okay? 1 over 10 to the n is equal to 10 to the minus n. And this is what we did just here, right? 1 over, for example, 1 over 10 is the same as 1 over 10 to the 1, right? 1 over 100 is 1 over 10 to the 2nd. 1 over 1,000 is 1 over 10 to the 3rd, right, and so forth. So that n in this case is just the exponent. So when we move that exponent over to the top, it becomes a negative, right? 1 over 10 to the 1 is 10 to the minus 1. 1 over 10 to the 2 is 10 to the minus 2. 1 over 10 to the 3 is 10 to the minus 3. So this and this is exactly the same number, as it is this one actually, right? They're all the same number. All of those are the same number. It's just different ways of expressing the same number. And we've chosen to use this notation to manipulate powers of 10. The rule also applies if the exponent is negative. So if you have 1 over 10 to a negative exponent, if you move that number to the top, if the exponent becomes positive. Okay? So this is the first rule. Okay? For example, in this case, we have 1 over 1,000. 1,000 is equal to 10 to the third. Well, 1 over 10 to the third is equal to 10 to the minus 3. The idea is that, and then the other one, just so we can finish this, 1 over 0.00001 is equal to 10 to the minus 5. Okay? Now, this is important that you can understand how to go from this number to this representation, because it's the same number. But we can go one step further and say 1 over 10 to the minus 5, when I move this 10 to the minus 5 to the numerator, it becomes a positive 10 to the 5th. The idea is that eventually this is the numbers we're going to be using. This is the type of notation we're going to be using, okay? So it's important that you understand that this expression 1 over 10 to the minus 5 is the same as 10 to the 5. Okay? So that's the first one. The next one is the product of powers of 10. So the product of powers of 10 means that if we have two powers, one is n, one is m, whatever those numbers are, if we multiply those numbers, as long as they have the same base, the base is 10, right? So 10 to the n times 10 to the m becomes 10 to the power of the sum of the two powers, right? In this case, n plus m. And again, it's very simple if we look at an example. Look at example 1.5. A. We multiply 1,000 times 10,000. Well, 1,000 is the same as 10 to the third. 10,000 is the same as 10 to the fourth. So according to this rule, n is 3, m is 4. So the result will be 10 to the addition of 3 plus 4, or 10 to the 7th. Be careful here, because a lot of people tend to make that mistake that since you're multiplying the numbers here and the base is 10, they tend to multiply the exponent, but that's not the case. When you multiply numbers of the same base, the exponents add up. They don't multiply, right? So be careful about that. Another example here, you have this number times 100. This number here represents 10 to the minus 5th, or minus 5. And this 100 is 10 to the second. So the same thing here, the base will remain the same, so the answer will be 10 to the, and we're going to add the exponent. So the exponents add up with the negative sign, minus 5 plus 2 becomes 10 to the minus 3. And that's the answer. Okay? So that's the second rule. Very important. Okay? The next one is the division of powers of 10. Divisions of powers of 10 says that if I have two numbers and I divide them up, and they both raised to some power, one is raised to the power n, and another one is raised to the power m, 10 to the n over 10 to the m, when I simplify, the base remains the same, but the exponents subtract. Okay, the exponents subtract. So in a multiplication, like the case we saw before, the exponents add up. Keeping in mind the signs that you have, right? When you divide powers of 10, the exponents subtract. Okay? So another example here, you have 100,000 over 100. Well, 100,000 is 10 to the 5th, right? There's 5 zeros, right? 10 to the 5th over 10 to the second. Well, when I simplify this expression, the 10 will remain because it's the same base, but then the exponents are going to subtract the top from the bottom. That's also important. You also subtract the top from the bottom. So 5 minus 2 will give me 10 to the third, and that will be the answer. And this is the same as really simplifying, because if you look at this original expression right here, the 100,000 over 100, right? If you simplify that, you can get rid of the 2 zeros at the bottom with the 2 zeros at the top. And when you get what? You get 1,000, which is 10 to the third, right? It's the same thing. We're doing the same thing. We're just coming up with a method that will help us later deal with a little more complicated problems. Another example here, you have 1,000 divided by 10 to the minus 4, right? So again, the base will remain the same, and now the rule says that I have to subtract the top from the bottom exponent, keeping in mind the sign. So since this is negative at the bottom, right, then when I subtract, it's going to become positive, and then you have 3 minus minus 4, and that will give me 10 to the 7. Okay? All right. Okay, the next rule says if the power of powers of 10. So if you have a number 10 to the n, and I raise that whole number to a power m, then the result is the multiplication of the exponents. Here you multiply the exponents, see? When you raise something to a power, you multiply the exponents. And it's very simple again. If you look at this example, you have 100 to the 4th. So 100 within parentheses is still 10 to the 2nd. So 10 to the 2nd raised to the power of 4 means that if I apply this expression, I'm going to multiply the exponent, so I have 2 times 4, or 10 to the 8th. See? Let's do C here also. Got 0.01 raised to the minus 3. Well, 0.01 is the same as 10 to the minus 2. So I'm raising 10 to the minus 2 to the power of minus 3. And if I follow this rule, it says that I have to multiply the two exponents, keeping, again, the sign conventions, whatever they are. In this case, I'm multiplying minus 2 times minus 3, so the number will become positive 6. Okay? All right. Now, we're going to look at some basic operations using this kind of numbers, these rules. But now we're going to have some number attached to those powers, or whatever the number is. In this case, they indicating those numbers as A and B. And it says, well, what if you have a number like 5 times 10 to the 1,000, right? Like this one, right? Well, that number is the same as saying 5 times 10 to the 3rd, right? And you have another number, 0.0004, which can be written as 4 times 10 to the minus 4, right? So what happens if we want to do something with those numbers? If we want to add them, subtract them, multiplying, or whatever, how do we manipulate those numbers? And if you follow this rule, it's also simple. And it says, like, if I have a number a times 10 to the power of n, and I add or subtract another number b times 10 to the same power n, the clue here, or the rule here, is that they have the same exponent, right? N is the same one. Then the rule says that I simply just add the a's and the b's together, and the exponent becomes the same. And this is what you do every day, right? If you add $100 plus $100, right? Then you have $200, right? Now, if in other words, you're keeping the same type of exponents together, right? You add ones to ones, tens to tens, hundreds to hundreds, thousands to thousands, right? If you add 1,200 to 300, right, you know that you're going to add the 200s to the 300s, right? So that's the same rule here. When you add numbers like this, the exponents have to be the same. Just the same rule. Remember, when you added numbers, hundreds to hundreds, thousands to thousands, units with units. So it's simple, and we'll look at an example here. So let's look at this example 1.8, and you add in 6,300 to 75,000. So the first thing I'm going to do is I'm going to write those numbers as powers of 10. So, and I'm going to keep those numbers of 10 to the same power, so I can apply this rule, right? So I'm going to express, in this case, I'm going to express the numbers as thousands, each one of them. So I have, if I write these numbers, especially this one, right? This one's already in thousands, 75,000, right? So this is already 75 times 10 to the 3rd. No problem here. This one, however, if I want to write it as thousands, right? I'm going to have to move the decimal point where between the 6 and the 3, right? So I have 6.3 times 10 to the third times 10 to 1,000. As you can see, this highlighted number is exactly the same as 6,300, right? And the reason I'm doing that is because, remember, I want to add thousands to thousands. I want to keep the exponents the same so that I can simply add 6.3 plus 75, see? And then the answer will be 81.3 times 10 to the third. Okay. All right. The second example, this one again, if I want to express the answer as 10 to the minus 5, I'm going to write both expressions in terms of 10 to the minus 5. And I can do the same thing here, right? If I do 96 times 10 to the minus 5, right? I'm moving the decimal point 5 places, right? Notice here, the decimal point moves 1, 2, 3, 4, 5, right? Right where the 6 is, I move the decimal point 5 locations, right? And since the decimal point has moved over to the right, then this is going to be a negative exponent, right? So I moved the decimal point 5 times, but it was already a number less than 1. So this exponent will be minus 5. The same thing here, right? If I move the decimal point 5 locations, it'll be between the 8 and the 6. So now I have both numbers as exponents of minus 5, and I can simply do the operation that indicates, in this case, a minus. So I'm simply going to subtract 96 from 8.6, and the exponent is not going to change, and this is the answer. Okay. Okay, so now we're going to be looking at the multiplication rule. You notice here the rules are the same as the ones we did before when we didn't have numbers in front of the powers of 10. It's different since now we have numbers, right? But the rules basically become the same. So what we want to do is, in the case of multiplication, if you have a number a times 10 to the n times another number b times 10 to the m, you're going to multiply the numbers a, b, and you're going to follow the same rule that we followed before. You're going to add the exponents, right? In this case, they don't have to have the same exponent when you multiply. They only have to have the same exponent when we add or subtract. Okay. So the rule basically is that when you multiply numbers in the powers of 10, first find the product of the multipliers and then determine the power of 10 for the result by adding the power of 10 exponents. And it's easier to do than to say it, basically. If you look at this example here, right? We multiply these two numbers in parentheses, and what I'm going to do is I'm going to put the number in powers of 10, each one. So, and to keep it simple, the idea is that I'm going to keep the expression as an integer multiplied by some power of 10, right? So 2 times 10 to the minus 4 is the same as this number because I'm moving the decimal point, remember, 4 places, right? In this case, it's a number less than 10. I'm sorry, less than 1. So if I move the decimal point 4 times, it's going to be a negative exponent. And it becomes a 2, right? So now I have 2 times 10 to the minus 4. I can do the same thing for this other number. I'm going to move the decimal point in front of the 7. So I'm going to move it 6 places. So I'll have a negative 6. And that's basically it. Now I have 2 numbers, each one a different exponent. I just simply multiply the numbers. The exponents don't have to be the same, remember, when you multiply. So it's simply as multiplying 2 times 10 to the 7. And I follow the rule for multiplication of powers. The only thing you got to be careful is that when you multiply in powers of 10, you add the exponents, remember? You add the exponents. So in this case, I'm going to add minus 4 minus 6, right? Because I added them together, or minus 4 plus minus 6, if you will. And this becomes minus 10. So the answer is 14 times to the minus 10. And I'm going to leave this other one for you as an exercise to make sure you get it. All right, the next rule is division. If you follow the multiplication case, it's very similar. And so let's do the division. And it's the same rule as before as far as the exponent, right? So what I'm going to do is, again, I have these two numbers, right? And I'm going to represent the numbers as integer. The 47 as an integer and the 2 as an integer. By doing that, then that means that I'm going to have to move the decimal point in front of the 7 or 5 places, but since it is a number less than 1, that exponent is going to be negative. So I'm moving the decimal point to the front of the 7, 5 places, so this is equivalent to 47 times 10 to the minus 5. Okay. Same thing for this number in the denominator. If I make it an integer 2, I'm moving the decimal point in front of the 2, 3 places, and it becomes a negative because this number is less than 1. So now I have 47 times 10 to the minus 5 divided by 2 times 10 to the third. So I can simply divide the numbers that I have outside the exponents, or the powers of 10, I should say. And then regular rule of division. And then for the division of the powers of 10, I follow the rule I know already, which says that I'm going to subtract the top exponent from the bottom exponent. So in this case, I'll have, remember, you got to follow the signs of the exponent. So I'll have minus 5 minus minus 3, or minus 5 plus 3, which gives me minus 2. See? And again, I'm going to leave this one for you, B, as an exercise for you to do, so you can practice. The next one is powers of in general. So if I have a number a times 10 to the n, and I raise the whole number to the power m, then the rule is simple. I'm going to raise that number a to m, whatever the power is, and I'm going to follow the rules of power for the powers of 10, which is multiplying the exponents. All right, so if we look at an example, I have this number 0.00003 raised to the power of 3. Well, then that number in parentheses, if I move the decimal point in front of the 3, I'm moving it 5 times. So this will be 3 times 10 to the 5th, minus 5th, or minus 5, raised to the power of 3. Right? So notice how I made this number inside the parentheses equal to this expression inside the parentheses, right? By manipulating where the decimal point goes. So this gives me this whole number is raised to the power of 3. So I'm going to raise each of the parts, the integer part, which is 3, to the power of 3, and then the power of 10 part to the power of 3, which is this part. And if I follow the rules as I did before, what I'm going to have to do is just multiply the exponents, right? So this will give me minus 15, and this will give me 27, and that's the answer. Okay. And again, I'm going to leave this B part example for you to practice. Okay. So be careful now, you know, with things like this. For example, when you multiply, for instance, 10 to the third times 10 to the third is not the same as this, right? You got to be careful. It's the same as adding the exponents, which will be 10 to the 6, right? So just be careful, you know, what you're dealing with when you have those exponents in that way. All right, so the next topic in this section, in this chapter, is using what's called fixed point, floating point, or scientific and engineering notation. For most part, if you're taking a course like physics, you already use scientific notation, right? It's just expressing some numbers as powers of 10. Engineering notation is a little different, and it's the one we're going to be using in circuits. Okay, that's what's important, that we use engineering notation when you work in problems with circuit analysis. But so fixed point and floating point, we're not going to really deal much with it. It's not what we're going to be using in this class, but it's introduced here as a basis for what we're going to be looking at in engineering notation. And all this fixed point, floating point, scientific, and engineering notation all has to do with where the decimal point goes. That's all it has to do with. Because where the decimal point goes help us in certain ways manipulate operations when we deal with numbers. So in the fixed point format requires that the decimal point always shows up in the same place each time. So it doesn't matter, how you add the numbers or what numbers you're going to add. That type of arithmetic or that type of math requires you to have the decimal point or the decimal point always in that same place. Okay, it's just the format you follow. In the floating point format, the decimal point depends on the numbers to be in the location of the number, where defined by where it's to be displayed. Most computers and calculators give you that option, right? Whether you want the answer as fixed point or floating point. For example, if you manipulating your numbers in your calculator and you always want the answers in thousands, right? It doesn't matter what numbers are, but you always want the numbers in thousands, then you choose the fixed point format and your numbers will always show up as thousands, right? In the fixed point location, however, that decimal point is going to change, right? That's the difference. Okay, so for example, in this 3 examples at the top is an instance of a fixed, a fixed point location. Let's go back here, right? Because in this case, every answer that you see has 3 decimal points, right? So it's fixed, right? 1/3 is 0.333 and so forth, right? 1/16, it always gives you the answer as 3 decimal places. Is that if that is what you have chosen in your calculator, for example. If you want your answer to always be to 3 decimal places, then your calculator will always give you answers to 3 decimal places. That's what fixed point format is, right, at the top. In floating point format, see, the number of decimal places or the number of digits after the decimal point varies, right? Like in this case, see how many digits after the decimal point? See, in this one, there's 4 after the decimal point. In this one, there's none, right? So this means that it's a floating point format because the decimal point can be in different locations, right? Okay, and that's the difference between fixed point and floating point. Okay, the other way of displaying numbers is using what is called scientific notation. It's also called standard notation. Those make use of powers of 10 and have restrictions of what the mantissa is the multiplier part, is. So scientific notation, and this is the rule for scientific notation, requires that the decimal point appears directly after the first digit greater than or equal to 1, but less than 10. So again, it simply says that the integer part of the answer, or in other words, the portion of the answer before the decimal point, always has to be a number greater than 1 or equal to 1, but less than 10. Okay, so the number right before the decimal point always is a number between 1 and 9. 1 and 9. Okay, so for example, if you look at this expression here, 1/3, right? If you're using scientific notation, then you notice that the numbers, like 1/3 is this number, right? But in scientific notation, the number before the decimal point is 3. So it's between 1 and 9, right? But then it gives you the expression, and in your calculator, E is usually what you'll see, and E simply means a power of 10. Okay, it's the same thing. So, and as you notice, the numbers are the same. Number is a number, right? 1/3 is the same as this, is the same as this, and it's the same as this. It's the same number. We're just representing the same number in different ways, but the number doesn't change, right? The nature of the number is still the same. 1/3 is still 1/3. It doesn't matter how you represent it, right? It just matters of how accurate you want the representation to be, or in what type of accuracy you want it. So again, if you write the number in scientific notation, then the mantissa part is the integer part here. It's always going to be a number between 1 and 9. And then what follows will, after the decimal point, will be our numbers, we need to whatever power that decimal point has to be moved. In other words, if you look at this expression here, if I move the decimal point 1 to the right, it's going to be right after the first 3. So I move it 1 after the right, but that number is less than 1, so the exponent is going to be -1, and that's what I'm doing here, right? Same thing here, right? If you look at 1/16, if I want to write it in scientific notation, I need to have this first number before the decimal point to be a number between 1 and 9. In this case, it's 6. And then, right, to move that number, because if you notice here, 1/16 is 0.00625. If I move the decimal point once, if I move it to 0.06 and then leave the decimal point there, it will not be scientific notation. Because scientific notation, the first number before the decimal point has to be either 1 or less than 10. So from 1 to 9. So I need to move it at least 2 times, right, toward right after the 6, and then, right, I'll have it as scientific notation, but I have to account for the movement of that decimal point by including the minus 2. Okay. So with scientific notation, the fixed or floating point format can be chosen. It doesn't matter, right? And then you can see here, you can write it this way, that way, right? It doesn't matter. If I use scientific notation with floating point, you notice that this decimal point can be moved, right? So anyhow, you notice that the main difference now is that with scientific notation, I'm using exponents, right, to represent the numbers. And with the next type of notation, engineering notation, I'm going to be keeping the same idea. I want to represent the numbers using exponents, powers of 10 to be more precise. But the difference now here will be that all powers of 10, there's 2 rules different from scientific notation. In scientific notation, the exponent that I can use doesn't really matter. Right? In this case, you can see the exponent is -1, -2, and it's 3. It could be any number. When I move to engineering notation, I'm restricted to what kind of exponents I can use. So when I move to engineering notation, there's 2 things that change. The first one is that the exponents that I'm going to be using can only be multiples of 3, or it could be 0. So it could be only 0 or multiples of 3. Okay, that's what confuses some people. So make sure you're understanding this. When I move to engineering notation, I can write the numbers only using powers of 3, multiples of 3, 3, 6, 9, 12, 15, whatever that is, or 0. That's the first rule. The other rule is that the mantissa, or the number before the decimal point, okay, can be any number between 1 and 999. Okay, so that's the difference. In scientific notation, the mantissa number before the decimal point can be a number between 1 and 9, and the exponent could be any number, any integer number. Right? See? any number. The difference now with engineering notation is that the number before the decimal point, the mantissa, can be any number from 1 to 999, and that the exponent can only be 0 or a multiple of 3. See? So now, if you use engineering notation with 2 places of accuracy, see, I can write the same number using engineering notation, but you notice here that all the numbers have power of 3. Now I want to remind you again, okay, that the number is still the same number. The number hasn't changed, right? 1/3 can be written as fixed point arithmetic, where the number of decimal places don't change. It can be written as floating point format, where the number of digits after the decimal point can vary. It can be written as scientific notation, right, where the first digit has to be a number between 1 and 9. Or it can be written as engineering notation, where the integer part can be any number between 1 and 999, but I can only use powers of 3. But keep in mind that the 1/3 here is the same number. It doesn't matter how I represent it, right? It's the same number. Okay? All right. Excuse me. Let's see, did we move? Let me go back. I don't know how I got out of here. I know how. Okay. All right. So I know it could be confusing with this notation, but what is going to help you here, and the only thing that's going to help you, is that you practice. Practice, practice, practice until you feel comfortable. What's important is that before we move on to the more complicated things in the next few chapters, is that you actually feel comfortable using this notation. Because if you don't, then you're going to stumble upon other problems, and it's going to stop you from progressing properly. So it's very critical that you practice this and you start feeling comfortable in using this notation. And we'll do more as we go along, but remember, it's important that you practice. The other thing that we're going to look at is look at prefixes that are commonly used in engineering. And some of these prefixes you already use. You use it every day, or in many portions of your life, right? Anytime we talk about millimeter, anytime we talk about micro, or gigahertz, or gigabytes, or megabytes, or whatever, that mega, kilo, giga, those are prefixes. Okay? We use those every day, and whether we realize it or not, we are using engineering notation. Those prefixes come from the use of engineering notation. Okay, so you don't have to memorize this. Some of those, it will be a good idea that you do, because as you progress and use this this notation, it's easier for you to memorize what that is. But this is a reference, right? For example, mega means 10 to the 6. Kilo means 10 to the 3rd. Milli means 10 to the -3. Micro means 10 to the -6. Nano means 10 to the -9. And you also see what they represent in terms of zeros after the decimal point, right? Or before the decimal point, whatever the case might be. Tera, like terabytes, right, means 10 to the 12, or 12 zeros, right? You can see that here, right? 12 zeros is terabytes, hertz, whatever the unit that you're looking at is. Giga is 10 to the 9 again, right? 9 zeros, right? So that's what that represents. It's just a shortcut notation to represent those numbers. But it's important that you know what those numbers represent, And also it's important that you see what the symbol we use is, right? When we talk about giga, we use capital G. Capital is important, capital. When we use tera, we use capital T. When we use kilo, we use lowercase k. When we use milli, we use lowercase m. Micro is mu, the Greek letter mu. Nano is n, and so forth. So it's really important that you know what symbol we are associating with what number, right? Really important. Some examples here. We have 1 million ohms. We haven't talked about what ohms are, but just, ohms could be anything at this point. But we have 1 million of those, where 1 million is 1 times 10 to the 6. Well, 10 to the 6 is mega, right? 10 to the 6 is mega. So we really have 1 mega ohm, and we use M, see capital M, to write our answer. So notice here that we're not going to really write answers like this, right? Well, when you say, let's look at this example to see that. Like you have 100,000 meters. 100,000 meters is 100,000 meters is 100 times 10 to the third meters, right? 100 times to the third, right? So that means that we have 100 kilo, because kilo is 1,000 kilometers, right? Now we won't leave the answer like that, but we will leave the answer like this. And those are the type of answers we're going to be using in this book and in electronics in general. We're not going to write down 100 kilometers. We're not going to write down 1,000 millimeters, or we're not going to spell that out. We're going to use the symbols to represent that, the proper symbols. Another one here, we have 0.1 times 10 to the minus 3 seconds, or 0.1 millisecond. Well, again, we're not going to spell that out as milliseconds. We're simply going to put a little m followed by s. Okay? So get used to that notation and using this prefixes and symbols, understanding what they use, what they mean. You notice here again that in our answers in this example, we only use in powers of 3, right? We use an engineering notation, right? Powers of 3, because this is what is the basis for this type of prefixes that we commonly use every day, right? So let's look at another example. A couple of other ones. I'm gonna do just a couple of them. I'm gonna do the first one. It says, well, the first one's too easy. Maybe the second one. We have 0.00956 J. J stands for joules. It's a unit of energy. Capital J means joules. Okay, so we have 0.00956 joules, which if I write it in engineering notation, which I should, means that I'm going to write these numbers, and before the decimal point, the number I'm going to use has to be between 1 and 999. But the other caveat is that if I want to use an engineering notation, the exponent of the power of 10 has to be a power of 3. Right? So if I move this decimal point 3 times in front of the 9, I'm moving it over to the right. And since it is a number less than 1, it's going to be negative. So I have 9.56 times 10 to the minus 3 joules. Notice that at this point, this number is in engineering notation because it's following the two rules. The rule that the mantissa, or the number before the decimal point, is between 1 and 999, and the other rule is that the exponent is a power of 3. So this number here is written in engineering notation. And now I can say, well, 10 to the minus 3 means milli. Because I know minus 3 means milli, because I know it from here, right? Milli is associated with 10 to the minus 3. So I have 10 to the minus 3 millijoules. Again, I'm not going to leave the answer like this, although it is correct. It's not proper. The proper answer is this. 9.56 little m means millijoules. That will be the proper answer. And I'm going to leave the other ones for you to test, but practice. But it's the same idea. Let's do one more. C, yeah, 0.000768 seconds. Again, I want to write that number in engineering notation. Notice that if I move the decimal point 3 times over to the right, I still don't have engineering. So if you notice here, you have this number, right? Right? If I move the decimal point 3 times over to here, right? Then I still don't have engineering notation because that number that I have before the decimal point is still less than 1, right? And the number has to be greater than 1 or less than 999. So I'm going to have to move it again a few, oops, excuse me. Go back. I'm going to have to move it 3 more times, right? Because if I move it 1 more time in front of the 7, it's not going to give me enough to have a power of 3 over here. So I'm going to have to move it 3 more times in front of the 8 here so that I can have a power of 6. And I have moved, when I move it all the way up to the in front of the 8, then this thing. When I move it all the way out in front of the 8, I have moved the decimal point 6 places, or 10 to the minus 6. And at that point, I have 768, and I know, and that's the notation I gotta start getting used to, that I'm not gonna leave the answer like that, even though it's correct, numerically correct, and it's in engineering notation. It's still not the proper right answer because I have to write it in terms of the prefixes. So 10 to the minus 6 is micro. So the answer will be microseconds, just like this. That's the right answer. Okay? So hoping that that give you an idea of how this works. All right, the next set of skills that you need to learn in order to start working later with circuit problems is how to go from one base or powers of 10 from one to the other. In other words, if I have gigabytes, how can I express that as megabytes? If I have megabytes, how can I express that as terabytes? If I have kilohertz, how can I express that as megahertz, and so forth, right? So so that's a good skill that we need to learn how to do. Well, let's look at one example here. And these are the rules right here, by the way, right? But instead of me reading them to you, you can read them by yourself later and make sure you understand them, obviously. I'm just going to show you by example. Later, you can reference this 3 little rules and see how that works. But by example, I think you'll be able to see it better at this point. In this example, we want to convert 20 kilohertz to megahertz. How do I write kilohertz into megahertz? Right? So the idea is that I want to go, that I have 20 kilohertz is the same as 20 times 10 to the 3 hertz, right? Because of the kilo. The kilo means 10 to the 3rd. So in this conversion, what I want the answer to be in megahertz, or 10 to the 6, right? So I really want to go from kilo to mega, or I want to go from 10 to the 3rd to 10 to the 6, right? So that means that if I want to make that conversion from kilohertz to megahertz, that means that I'm increasing the exponent from 3 to 6, right? I'm increasing the exponent from 3 to 6, or by 3. So if I increase the exponent by 3, I'm going to, in this empty space here, which will be the my transformation of this number, so it maps megahertz, is that, of course, in this number here, the decimal point is right after the 20, right? It doesn't show it, but it's right there, right after the, right after the 0, right? So that means that I'm going to decrease the decimal point by 3. Right? So then I'm going to move the decimal point, see, is in front of the 0. I'm going to move it 3 places over to the left, right? 1, 2, 3, or at 0.002, 0.02, right? So let's go over it again, right? I'm going from kilohertz. I want to represent 20 kilohertz into megahertz. Well, what that means is that I want to go from 10 to the 3rd kilohertz into 10 to the 6th megahertz, right? That I know. I know that the exponent is going to be a 10 to the 6th because that's what the problem wants. What I don't know is at this point is exactly how this other part is going to look like, right? The underscore part. What I know is that in going from kilohertz to megahertz, I'm increasing the exponent by 3, see? It's going up by 3. So if I increase the exponent by 3, to compensate, I'm going to move the decimal point by 3 over to the left. And that's what I did right here. I moved the decimal point from being in front of the 0 over to the left 3 points or 3 places, so it ends up right here. And so the answer is 0.002 or 0.02 times 10 to the 6 hertz, or, which is the correct answer, 0.02 megahertz. Right? And that's really the rule always. If you increase the exponent, you decrease the location of the decimal point by the same number. See? Increase the exponent by 3, I decrease the location of the exponent by 3. All right? Let's look at another one. All right, this one says convert 0.01 milliseconds to microseconds. And again, that's what's important to understand what those milli, micro mean, right? Because we can then translate that into actual powers of 10. So what it's saying is that I have 0.01 milliseconds. Well, 0.01 milliseconds is the same as 0.01 times 10 to the minus 3 seconds, because that's what milli is. 10 to the minus 3 is milli. And I want to write the answer in microseconds. That means that I want to write the answer as 10 to the minus 6, because that's what micro means. Micro means 10 to the minus 6. So I want to go from 0.01 times 10 to the minus 3 seconds to something that I'm looking for times 10 to the minus 6 seconds, right? So the first real important step is that you recognize this relationship here, right? So now I have, if you look at this expression, you notice that you go from minus 3 to minus 6. And that's a decrease, right? Because it's negative. It's going down even more. It's going more negative, right? Remember the number relationship in the linear scale, right? Numbers over to the left. As you go further and further to the left, the number becomes smaller and smaller, right? And so in this case, you're going from minus 3 to minus 6. So you're decreasing by 3, see? So if you're decreasing by 3, you're going to increase the location of the decimal point in this part by 3, right? You compensate, see? In this one, you were increasing by 3, so you decrease by 3. In this one, you decrease by 3, so you're going to increase by 3, right? So now you're going to increase the location of the decimal point 3 places, and it ends up being right after 1, 0 right there, right? So then you have 10. By moving it 3 places from here, if I move it 3 places over to the right, I ended up with 10. And so the answer is 10, now 10 to the minus 6 seconds, or 10 microseconds. All right. So again, practice this. It's really important that you keep practicing. Okay. Okay, guys. The only other section left in this chapter has to do with the conversion within and between system of units. I'm really not going to cover it. This is something that, you probably know from your college math. But it's important that you know how to do this kind of thing, right? To convert, if you want to go from inches to feet or from meters to feet or vice versa, whatever. Excuse me. That's the kind of thing that this unit deals with. It's important that you know how to do this, however, because in many cases you're going to have to go like from minutes to seconds, from seconds to minutes, that kind of thing. So this type of conversion is something that I assume you did this kind of work in your high school math. But if you haven't, or if you need a refresher, it's important that you review this section, okay? There's an appendix in your book, in the back of your book, that has a lot of this conversion of what a meter is in terms of feet, in terms of yards, that kind of thing. So that's something that you can use as a reference. Other thing, remember, it's important that you know some of the symbols, like in this table 1-3, right? Again, we're probably not gonna use all of them, but it's important that you understand how what they mean, this kind of symbols. If you need any refresher, if you have any questions about these examples, you can always email me, okay? Again, important that you get your calculator if you haven't gotten it yet. It doesn't have to be the same type that is listed here, but it's something that is scientific, like I mentioned in the previous video. And more importantly, that you really feel comfortable in using it. Because once you start working with problems, once you start working on tests, using the calculator is going to really be important, and it doesn't have to be a problem for you to use it while you solve problems, or you work problems, I should say. Okay. All right. So that's all for this chapter 1, and we'll see you on the next one.